Hello everyone, welcome to the presentation of Team ANTRIX and Satellite category for the Space Science Challenge 2021 organized by Spaceonova. Team ANTRIX, our model is in tribute to the flying Sikh of India, Mr. Milkha Singh. Our project title is Strengthening Deep Space Small Satellite Missions powered by solar electric propulsion with effective management using microfluidic heat exchangers. Our team members are I, Ms. Ishita Bhatnagar, Mr. Anand and Mr. Sandesh Khede. Why is the need to explore? Curiosity had its own reasons for existing. Maybe our reason to think, our reason to explore, or our reason why we do all the things. As said by Galileo Galilei, F4 is still moving. Yes, it does move. This is a storyline for our presentation. Satellites. So what are satellites? They are the communicator which sends signals, images, weather forecasts, preliminary data, and other details used by the geologists, scientists, and even sometimes in different sectors. In simple terms, multi-purpose space-flying tool consisting of various avionics, payload stages, and which gets implanted in orbit, serving the purpose. Also a dockable device is called a satellite. As the problem statement goes, we are working on strengthening deep space small satellite missions which are powered by solar electric propulsion with effective management using microfluidic-based thermal systems of microelectronics which plays a crucial role in exploration. As we know that deep space missions are the need of time and would be a booming area of interest in coming times, we aim to use the propulsion systems or subsystems for those. Just like the Voyager 1 and 2 which became the first to cross the interstellar boundaries, our system would do the same. The current functionality of proposed solution. As said in previous slides, our design would work on the subsystem or principles of the microfluidic and microavionics elements. This is the parametric model of a satellite. On the left-hand side is the SolidWorks model, where the right one is the rendered one.
Thank you, Ishita. So as discussed, the ingenious key concepts of our Flying Sikh 1 is the solar panels, the ion propulsion, and the thermomicrofluidics for thermal management. Above the list of components for our satellites, we are using the solar ion thrusters, the AOCS, the miniatured optics with spectrometers, the deep space transponders, the car band solid power amplifiers, the beacon monitors, the power electronics, the multifunctional structures, and the spacecraft onboard computer and auto navigation. Also, we will be equipped with the multiple docking system, thermal control system for our satellite. So about the microelectronics and the microfluidic thermal management, over to Santesh.
Thank you so much, Anand. So, even though there will be microfluidics-based systems to thermally manage the microelectronics, however, the satellite will also have the existing thermal management systems, which will be actively and passively pumping out heat using conduction and radiation to store heat, collect heat, reject heat, and transfer it wherever needed. And the typical existing systems that require the standard thermal management systems are the traveling wave tubes, the electronic power conditioners, input filters, output multiplexers, the various microwave equipment which are used for the ion propulsion systems, as well as transponders, receivers, primarily also the data processing units, batteries, optical sensors, the solar power generators, and the propulsion pipelines. So typically, microelectronics are primarily in the areas of systems on chip, chipsets, which we are very well known in the form of ASICs, FPGAs, which are the building blocks of these satellites, because they overall help in the miniaturization of the electronics and leave enough of additional space to increase the functionality of the satellite. So typically microprocessors, microcontrollers, bus nodes, routers, which are used in telemetry, telecommunication, primarily for digital signal processing, controlling and pointing the camera, telecom radiation detectors, and image sensors. So in addition to the existing type of microelectronics, they have also been evolved into advanced instruments. For example, miniaturized chip-sized spectrometers, also avalanche diodes, which are very highly sensitive photon diodes that help in optical communication of terabyte worths of data from the satellite to Earth stations itself. and likewise for bolometers, magnetometers, RF amplifiers, and high-powered computing systems. Now, what happens is a typical microelectronic circuit, instead of using the existing system of heat sinks and fans and other large-sized systems which would occupy space, here the cooling channels will pass through the microelectronic circuits, and the coolant will be basically few microns away from the actual hotspots which are being generated due to the operation of the microelectronics, and that will lead to a much higher and more effective heat transfer due to the high surface area. As you can see, where 1700 watts per centimeter square worth of heat flux can be removed just by 0.57 watts per centimeter square of pumping power, and also how an FPGA, which usually reaches 60 degrees Celsius via air cooling, can be brought down to 24 degrees centigrade. So for this particular project, we'll be making a computational model to study how a typical microelectronic circuit would have these cooling channels flowing, and coolants like deionized water or other easily available coolants which are affordable, how the heat flux and the heat transfer would be conducted. At the same time, if there are in case any thermal or thermomechanical deformations that could take place while the heat transfer is going on due to the fluid flow. For our electric propulsion, we are going to be using the Vasimir thrusters, which are variable impulse specific magnetoplasma rocket thrusters, which basically use electromagnetic radiation based heaters to heat an inert propellant, which will generate into plasma, and then via strong magnetic fields will be used for producing a thrust. A typical Vasimir thruster has around 1 megawatt of power capacity. Next.
Thank you, Sandesh. So as we know, power and communication plays the vital role of our satellite. The solar concentrated array with enhanced power solar system would be providing the electrical power for our satellites. And the small satellite Ka-band deep space transponder will be used as a radio communication system for efficient communication with our satellite. So about the system architecture, the high concentration photovoltaic cells, or the HCPs, unlike other conventional photovoltaic systems, it uses lenses or curved mirrors to focus sunlight onto small and highly efficient multi-junction solar cells. About the communication system, the curves above are the Ka band. At higher frequencies, the wavelength allows proportionally smaller and lighter weight and less expensive transponder in our satellite. Effectively, this would provide a better communication at a 3.5 gigahertz bandwidth. About the reliability and performance of our satellite, the overall model consists of a technological demonstration of fully autonomous planning, diagnosis, and recovery of data of the satellite. The universal spacecraft dockable module is the X factor for our satellite so that we can increase the deep space missions. The focus of the mission phase is on the ion engine thrusters. Also, the returning valuable science data and images will be crucial for our satellite. The space contains of electromagnetic radiations as well as ionizing radiations. We tend to use our microfluidics to protect our satellite from these radiations and make it work efficiently as possible.
Thank you, Anand. As per the market analysis and the economists, the price and the income for the global small satellite market is about to increase as the trend from the year 2018 to 22. By the 2026, we can see here a comparison for the market from 2018 to the predicted 2026.
Thank you, Shita. So as per Morgan Stanley's report, by 2040, the space market would grow up to $1 trillion with a CAGR of around 6.5. That would be primarily because governments would be expanding their budgets. A lot of private equity partners, investors would be involved, as well as a lot of private players would be coming with new technologies which are far more easy to be developed. And as discussed, reliability will be very critical for various forms of radiation, shocks, vibrations, and thermal instabilities, and for which microelectronics will be the essential building blocks to reduce size, make an affordable budget, and increase various functionalities.
Thank you.
Thank you.